Simulation by deep learning or simulation with deep neural operator is a method that uses only data to actually perform the simulation. In this method, we don't really or we don't directly give the the neural operator, the actual equations that is needed to calculate the value that we want to calculate. For example, solving the heat equation, it will be, for example, the temperature distribution. We don't directly give him or give it the relationship between space, time, and temperature. Using data only, it will get kind of understanding of these relationship through the applying neural operator. So first we say neural operator. What is operator? Why we call it operator? Why don't call it, for example, function? The reality is, we can't say a function is a specific or a very small case or a special case of operator. Operator is just a mathematical operation that is going to be, or in our case, represented by neural network, by deep neural network. So an operation can be getting a value of a function. For example, if you have x, we want a value y through f of x, well, a function. This is a mathematical operation that using a function, we can connect a value of x with a value of y or with a value of f of x. Now, operator is not just, of course, a function. Operator can be wider than getting a value through a function. For example, we can do a derivation. This is also an operator, or integration. This is a mathematical operation that using this operator, which is in our case a deep neural network based operator, we can do this computation or get the integral for any function we have. So in our case, we will have a little bit more complex mathematical operations in which we have a system that we need to simulate. This kind of system, in usual case, we will have, well, a series of mathematical operations to get the or to solve this mathematical function or the simulation problem we have. And in our case, using a deep neural operator, we can do or perform this simulation by only numerical, by only the deep neural operator. So basically, if you have an input function, an input curve, we will get through the operator, we will get an output function. So it is very wide, and it is a way for us to generalize how to, for example, integration. If we have this kind, let's say, of function, what we will find is we will have, for example, if we look at this blue function, if we want to integral this function, we will find that the first is this area under the zero line. We will have a minus area, and then we will have a little bit increase in this value here in just a little bit. So this function will go a little bit higher, and then this area going to be minus, and then it will go lower and then go upper. This is integration, numerical integration. Through the neural operator, we can perform such thing. So in summary, or in a short answer, operator is just a neural network, or deep neural operator is a neural network that can do a mathematical operation. So if we have integration in, as I said, this example, we will find that from, for example, this input function, rather than having an ordinary differential equation solver, for example, this one, we can employ a neural operator to actually do this job. Now, because it's a neural network and we're only relying on solving the neural network, only relying on or converging a neural network, we need data. So in reality, we will get lots of lines that we give it examples to the network, and then the network will using usual or machine learning methods, the loss will decrease and the weight will balanced, and with the values of them is correct. So we can give it a new function that is never seen before, and will give us the actual integration of it. So how to do this? How to train this network in steps? Of course, now we have more idea how can we do it, but in steps, what we need to do is first creating data. As we said, we don't give this network anything related to the physics, how these variables are related to each other. We just don't give it. So what we have to do is to give this network data, lots of data, as much as possible. And we will do it in this course, and we can see actually the how can we enter, how many datas we need. And because this is the problem between of new deep neural operator is we're not relying on giving the neural network the actual physical system, how it's related to each other. So we will find out that we need a lot of data, especially when the things become more, well, the simulation environment become more complex. For example, if you want to solve Navier-Stokes equations or a fluid-based equation, then there are lots of variables, and then we will need a lot of data, and it is going to be a problematic. This is what we will see in the one of the our or the last example of what we have. So after you create the data, what you will need is you need to pre-process it. After creating the data, we need to pre-process it in a way that is suitable for a neural operator. And we can see it is a little bit different. How can we enter the data into this neural operators? Once you enter it in the correct format and you create your data in the correct format, you will build a deep neural net. This deep neural net we will build in our in this course. It will be a quite simple neural net. But however, things will get complicated, and as any deep neural network problem, depending on the problem, you will require different types of neural networks, and this is of course um, an evolving domain, and you will find that there are many research papers, or some research paper, I would say some is better than many, some research paper that is related with the research of what kind of neural networks is suitable for what kind of problems. And as I said, like the reason I said some, because this domain is very new, and this is why you don't find many references. So after that, you will train the model. Training the model is as training any network. Reduce the loss as much as possible. You have training data, you have loss data, you have testing data, and you try to reduce these losses. You optimize your network to work well on the training and test the values on the testing set. And with that, you already finished training the network. After that, of course, you have to evaluate your results by giving the network a data that never been they never seen it before. The network never seen it before, and you evaluate how good your computation or how good your network is, and what kind of errors you might have. So in general, a neural operator, what we will give it at the end of it, or after everything is done, you will get a trained operator that we will give it an input function or an input well, initial condition, and some, let's say we need the solution at this time depending on the problem, and we will get an output of this operator. So one of the well, very famous operator is the DeepONet. The DeepONet is well, the main idea of it is basically we will use two networks. The first network is going to be branch network, and the second network is going to be trunk network. The branch network is going to take the whole function, the whole input function. So we will take every point in the input functions. For example, the initial condition, for let's say we are doing a simulation for heat equation. We'll have the initial condition of this heat equation, and then we want to predict we want to predict the result at specific x, the space, and a specific time. So, so we have to put this condition in the trunk network. So we're talking about x and time, so it has to be x and t. If you have, for example, only this function, you will, let's say you have one line, and then in this line you will have all of these values of this line that is going to go into the branch network. On the other hand, you will go to the location you want to calculate this number. Of course, in our case, let's say in usual case, we will have x and t. So we will get these at the location in which you are trying to get the value based on this initial condition, and it's going to go to the trunk network. These two networks will give us, well, some latent space. We call it a neural network, which is just numbers that represent the input location you want and the whole system or the whole initial condition. This latent space, we're going to dot product each other in operation we call Einstein product. We will see it in the later like in this course, but basically we'll dot product these two latent spaces, and we will get a final S of t. This number we will basically we will relate this S of t with the actual value that you need to calculate at this specific location. So we say we can enter x, we can the location of x, we can enter the time we need this location of x, and we will get the output in which the value at this location. If you have, for example, an integration, you will have an initial function, and then you will put the location in which you want the value of that point, and you want to predict s, which is the actual value. So you will have a different function that is related with this function as its integrator. So basically, this is how this network works. Well, most of the time, or in this course, all of the time, we will enter this way, like we will enter the whole initial condition, and then we will enter the location in which we want to get the value we want. And we will balance this with the output condition or the already integrated function that we will get it from different source, for example, numerical integration, or if we have heat equation, we will actually solve the heat equation, or if it's fluid dynamics, we will just get the results of the fluid data. So this is what we are going to do. And the thing is, as you can see, that the idea is of the DeepONets is basically you need two networks or two systems or two informations actually to the network. The first one is the whole domain. The second information, the location in which you are trying to perform you want to predict this value. So you will need the whole system, the whole initial condition, and the location in which we are trying to predict. You can enter it in one shot without branch and trunk, just into the network, and you will get basically its related data. So it's always where the whole system and the locations in which you are trying to get the function or the value. You will get up some curves at the other part of it, and then these curves has to multiply each other to get the outer value. Now, in the other configuration can be at every point will have a branch network. So every point of the whole function will go to a branch network, and at the end you will get this big latent space, and the same thing, the location in which you're trying to get the value, and then you multiply it to each other. So it, all of these, this is just architecture. Now, in my case, like, or in our case, this architecture is, well, the most common, and I really like this architecture because it separates. First, you will get a network that will take the whole system, the whole like time series, the whole input system, either it's time series or it's initial space like 2D or even 3D, doesn't matter, just more complex become. And then you will have a branch network, that this branch network is going to learn this line, and then you will get this latent space. On the other hand, the trunk part of this will get the location in which you want this value to be calculated at, and then you will have another latent space, you multiply each other, and then you reduce them to the final value. So this is another way of performing this work. Finally, let's just view the actual, basically the paper, the DeepONet paper. We can see this is DeepONet learning nonlinear operator for identifying differential equation based on universal approximation theorem of operators. So this is the paper, it's 2020, and you can see the authors. The first one is Mr. Lulu, or I'm not sure if he may be Dr. Lulu, and we have another guy here, Jen, and we have this Professor George, and you can actually type his name. You can see him on the in the YouTube's interesting person. And there are some lectures we have. This study is a collaboration between US and between Brown University in US and China, basically the Chinese Academy of Science. You can see it in like in these both respected institutes. So here we can see the of course the abstract. What we care about is these way of applying it, which I showed in the well, in the slides, how can you apply it. Again, the main idea is a network should know the whole system plus the location which it needs to calculate. So they apply it on two systems, like the DeepONet. They apply it on a physical system, I think this one, nonlinear dynamic system. So they apply this network on this problem, and then you can see here they perform integration, and just they show some results. And the other one is, I think, diffusion, solving diffusion. Like here also, gravity pendulum with external forces you can apply. Again, this time we're not really putting the equations, we just generate the data that actually going to go to the deep neural operator and then get solved there. So here you can see the different input functions and the output of these functions. So it's most of the paper is just talks about these errors and behaviors of these. Just some examples on the DeepONet. Here, the fusion reaction system. Also, this equation now they solve it. We have well, we're trying to solve S. We have time. We have X. So it's a good like basically input is X and T. So it's, I think, 1D, and you can see here the data like UX start from here. UX, you can see this this is here start, and then as time progress, this is going to be the solution. So we will do similar work in this class, but anyway, you can see this paper, and as I said, like the main idea of this paper, at least in my evaluation, is you need a network that knows the whole system, or the whole the whole initial condition, basically, and the location in which you want to calculate this thing you want to calculate in the future. This is what you need. I think this is the critical idea behind all of this work. And of course, after that, after this paper, we will see, or we can see some papers that also made such work, but well, they make the neural network a bit more complex, but it is still, I would say, similar idea. The network has to learn from the whole data and the location in which we're trying to calculate. Now, in this paper also, we can see, this is also a bit important. We can see, I think, in GitHub result or GitHub referral. I think in the conclusion, get, yeah, here, not in the conclusion, but here he's giving some basically references for this well, deep XDE basically, and you can see here the actual, this is the GitHub of well, related to this paper. You can see some examples is in here, like for example operator. You can see different way of applying it. However, of course, in our course we will use PyTorch. At the beginning we have to write our everything by ourselves, and later we will use DeepXTE, and we will use DeepXTE for solving the heat equation, exactly the same problem we solved with PyTorch, and with well, modeling a fluid system. So these codes, our code is not here, so we will find it. However, if you're just interested in seeing some of their code, you can find them here regarding the DeepONets. So let's work together and understand the problem of DeepONets.